Good morning, everyone. I hope that you guys are having a good start to your February and a good start to your Monday. I am doing all right myself. I just finished up one class and here I am for this one. Um, so what I wanted to first talk about was an announcement that I sent out last night. For starters, it looks like we've gotten, you know, folks have gotten the SSO sorted out. Really relieved and happy to see that because, in my earlier class, I didn't want to see like 15 people emailing me, I can't get in, I can't get in. So I'm happy that the Texas State IT department has some good directions. The next thing that I wanted to talk about was an announcement that I sent out yesterday about kind of participation and late work. And I alluded to this, I think, last Wednesday, but I wanted to add some clarity. And that is late work. So assignments that I will be assigning to you guys later on and relatively soon. I'll give you the timeline on when those are due, and I will say, oh, it's due at this time. But I'm always going to give basically 48 hours after that due date as a time in which you can submit it, but with a penalty. Um, Now, with that said, that penalty will be in the syllabus. In my initial draft of the syllabus, it said 25% deduction if it's submitted late. Um, but that's not a way that Canvas is capable of like assessing a penalty. And instead, the way that Canvas has to do a penalty is by daily. So I made a change where it's like if you submit it within the first 24 hours after the due date, you'll have a 12.5% point deduction. And then if it's within the first 48, but beyond the first 24, then it will be a 25% deduction. So if something's due on Friday night at 11:59 p.m. and you submit it at Saturday like 1:30 in the morning, um, you will have a 12.5% deduction. If you wait until Sunday morning at 5 a.m., then that will be a 25% deduction. If you wait until Monday, well, the window to submit it has closed. If you have any questions about that, please let me know. That is going to impact quizzes as well as assignments. So quizzes you'll be able to do, like we have a quiz that went live this morning at 8 over last Wednesday's stuff. That quiz will be open or it will be due at 11:59 p.m. on Wednesday. After that, it's late. At Friday or on Friday the 6th at 11:59 p.m., it shuts down completely. So you can't submit it after that. I hope that makes sense. Then the next thing that I wanted to mention was about Zoom participation. Um, Basically, what I want you to do is look at each Zoom meeting as having three parts to it in terms of like polling. I'll ask questions in the chat, and those are my informal questions. And those will be like the hey, respond with an X or respond with a Y or an N or a number or something. Those are basically just like, hey, are you here? And kind of, I don't want you guys to just be like, we just have to wait till the Zoom question pops up, done, click, done. I don't want that. I want you to, have these kind of low level questions where it's just like, hey, he's asking, is it A or B? Um, those are like kind of conversational questions. There are also going to be Zoom poll questions. I want you to treat each class as having three types of Zoom poll questions. The first type is the opener questions. Those will be typically within the first few minutes of class. We have not done them yet. After I'm done talking, I'll open them up. Those will stay open for about 5 minutes. And usually that's going to be about two or three questions, really assessing do you have any background on this particular topic? Is this something that you have some familiarity with from any other part of your life? Then there will be a couple of questions peppered throughout the lecture. Those are going to be what I'm referring to as the mid questions. And those usually I'll have like 3 to 5 of those. Today, we're not going to have any of those. And I'll talk about that in a little while. And then the last chunk of questions are the closer questions. The closer questions are, hey, we've talked about all this stuff. Can you apply that knowledge? Or, another way of thinking about it, are you ready to apply that knowledge? Um, if you're thinking, okay, well, what are going to be valuable ones for an exam? The ones that are valuable for an exam are going to be the mid questions and the closers. Those two are going to be the most beneficial because those are like applying the knowledge and applying the information that you just looked at. So now a great question there is, okay, well, that's great, but how does this contribute to my grade? Well, Zoom participation is worth 2 points a day. If you answer the openers or the big word there is or the mid questions, or the closers. That's worth 1 point. So if you get into class and you answer the opener questions, and then you're like, I got a doctor's appointment, got to go. You'll get one of the 2 participation points for that day's Zoom meeting. Um, Next option is, well, let's say that you answer a opener question, or you answer the opener questions, and then you miss all of the mid questions, like miss being you don't answer them, but then you answer the closer questions. You'll get full credit for that. What about if you answer the openers and then you hang around for one of the mid questions and then you got a doctor's appointment? That would be full credit for that day. So we've got these 3 types of questions: opener, mid, and closers. If you answer or participate in 2 of those, you're good. Now, does could I get a Y? Yes, I follow, or N, I don't follow. And then if you have a separate question, feel free to ask either in the chat or unmute yourself. I have a little connection. I have little connection. You are cutting out at some moments, which makes it so I can't see your screen that well. Will that affect the poll questions? It's a great question. I don't think so, because the poll questions are like a separate thing altogether. And actually, we're going to go ahead and test that right now. Doesn't seem like anyone has any confusion about that. As the semester rolls on, if something does surface, please don't hesitate to ask. I'm going to go ahead and throw the opener questions up right now. And these opener questions I'm going to leave up for the better part of about 5 minutes. Today, it's only 2 questions. In the event that you're like, how do I see those? They didn't pop up on my screen. If you're on a mobile device, or if you're on a laptop or a computer or a desktop, in the Zoom app, there's a button that says more. It has a circle and then it has 3 dots in it. You want to click that, whether you're on a mobile device or on a computer, and that will bring up, there will be an option or a pull down menu that has polls in it. You want to click polls. And whenever you click polls, then that will take you to the poll questions that have been asked. I'm going to leave these up for 5 minutes, but in the meantime, I'm going to go full screen because what we're talking about today is organic chemistry again. And what I'll do basically is put the questions up, then I'll talk about, then I'll kind of get started on the lecture, then I'll talk about those questions and show you guys the results. Okay, so organic chemistry, we're back. We started this last week, and we're going to continue knock this one out today. There are no mid questions today, so I'm looking for you guys to participate in the openers or the closers, and then you'll get full credit for today. That won't always be the case, but looking for participation in one. Okay, so organic chemistry, we're going to jump ahead a little bit. Here's sort of what we were talking about last week. And one of these things that I wanted to circle back on was this topic of hybridization. Oh, rats. How did that happen? Okay, so okay, so having computer related issues that did not happen at all in first class of the day, but they decided to resurface here. That's frustrating. So what we were talking about was hybridization. And we had previously talked about orbitals and subshells and where electrons were found and stuff. And this brought that topic back where we were talking about um, I'm sorry, everyone. This is um do a different way. Close that. Okay, that's fine. This PowerPoint's still open in any fashion. And you know what? Maybe that will help. Okay. So what we were talking about last week with this hybridization was we were looking for a question of, well, how do you have electrons in an S subshell shared with an electron in a P subshell? And you don't. What you do is you have to kind of take an S subshell and a P subshell and merge them together. Now, the important takeaway for you guys was how do we explain this idea, this topic? And the way that we explain it is by making a what's known as a hybrid orbital. Now, for our class, what's important is I want you guys to think about this as, well, how many things is my atom bound to? And I'm going to use just a model here. I'm going to use atom A being bound to molecule or atom X, I'll say. Okay, so A bonds to X, A bonds to X, and then A has one, two, three, four. It has two lone pairs of electrons. Okay, so my question for you guys is if a bonded atom is a thing that A is bound to, so this right here would be one thing, and a lone pair of electrons is another thing, how many things do you find around this atom A, this central atom A? Four. Absolutely. Okay. Now, whenever you are asked a question about hybridization, the kind of, I hate to say hack, but the way to do this is to simply ask yourself, how many things is this bound to? And you can use that to come up with, well, how do we hybridize this? So this A is surrounded by four things. Two of them are bonded atoms, and and two of them are lone pairs of electrons. So what we're going to do is we're going to count up S, P, P, P. Okay. Now, if we were to look at something like NH3, NH3, also known as ammonia, has three hydrogens and a lone pair of electrons. Tell me the hybridization of that right there. sp3. Great. Now, what if we had NH4? Oh, well, first of all, are NH4 and NH3 the same thing? No, they're different. One has three hydrogens, one has four hydrogens. Different. Um, do they have the same hybridization? Absolutely, because they both have four things around them. Now, I would highly recommend that you keep these as a good combination of examples to think about whenever you're prompted with this question. The reason being is this gives you a good comparison between a lone pair of electrons and a bonded atom. They're both treated as things that surround that central atom. Okay. So then what we talked about was we got into organic compounds. There's tons of different organic compounds. Now I'm going to take a pause there and I'm going to go ahead and end the poll. I got 96% of the class responded. I'm going to share your results. Which of the following is the best example of organic chemistry in everyday life? Table salt dissolving in water, rust forming on an iron nail, or ice melting in a glass? Well, the correct answer is that third one, gasoline burning in a car engine. Now, has anyone ever gotten gas? Oh, am I recording? Sorry. Yes, I am. Good. Um, has anyone ever gotten gas and you look at the when you go to the pump, you see something like 87, 89, 93. Does anyone know what those are? So, I mean, one way to look at it is cheap gas or expensive gas. And whenever I take my 1987 Honda Accord, I get the 87. But whenever it's time to take the Lamborghini out, well, then I get the 93. I don't have a Lamborghini, nor do I have an 87 Honda Accord. But those numbers, 87, 89, 93, that's pretty much the common combination of numbers in Texas. They have to do with like different kind of qualities of gas. There's unleaded, super premium unleaded. And those numbers correspond to something known as an octane rating. So basically, yeah, the makeup of the gas. I got that as a private message. You're absolutely right. The makeup of the gas. Essentially, how clean the gas is. And it's not a question of like, well, is one really dirty and one really clean? It's, I would say yes and no. Um, for most, to my knowledge, and I'm not a car person, nor am I much of an organic chemist, biochemist, is what I am. If you get 87 or 93 and you put it into, a Toyota Camry or something like that, a pretty well designed, mass produced vehicle, it's not going to, you're not going to get much more engine life out of that car. High performance cars like Lamborghinis and other high performance cars, a Maybach, yeah, we'll go with that, or a Bugatti or something like that. You got to get like 100 octane rating. And that's because those engines are very sensitive and touchy to like any level of contaminant. Um, what are the consequences of those? I don't know. I have yet to encounter that in my car owning life experience. But if I ever get a Lamborghini, um, there will be signs. And I will be very, very concerned with octane ratings and where can I drive my Lamborghini? But that's not today. So the next question is, um, so I'm bringing up octane rating because on the next slide, we're going to see oct as a prefix. And we've already seen that. But which everyday item is primarily considered an organic molecule? Baking soda, sugar, table salt, or sand? This is one that the most popular answer was the correct answer, sugar. So that's good that you guys know that. I think the table salt and sand, those were the least popular answers, and I think that those were kind of like, well, yeah, that doesn't have much carbon in those, I don't think. Um, but I'm happy you guys kind of saw through the other options. Okay, so our stems for organic molecule names. So this all relates to the number of carbons that are found on a molecule. Oct relates to, well, a substance with 8 carbons. Um, Octane, the octane rating of a gasoline. Well, how much octane is in there and how versus any other sort of relative impurities? Um, Methane, ethane, propane, butane, pentane. I think for the most part, lots of these numbers are going to be, or lots of these prefixes are not too much of a stretch. Specifically, pent, like a pentagon, hexagon, heptagon, octagon, nonagon, decagon, if you've ever like thinking of geometry. The meth, eth, prop, and but, though, those are a little bit, from my experience, those are a little bit tricky. I have to sit whenever I'm, kind of rattling these names off, I always have to do like a double take whenever I'm splitting between propane and butane. And I'm like, wait. Okay. Um, Now, one thing that I want you to think about with respect to these, though, is are there any of these prefixes aside from octane that we've already mentioned that you've maybe seen before? For instance, if you're a person who likes grilling, what do you get? Well, yeah, somebody added a private message and they said butane. Yeah, a butane burner, or you can get propane for your grill. Um, those are both flammable gases. And those names, those kind of market or shelf names, correspond to the organic compounds. Um, Now, when we write these compounds, I want you to be familiar with all four of these different ways of displaying or noting an organic compound: the molecular formula, the condensed form, the complete structural formula, or the structural formula. What I would like you guys to do and be comfortable with is starting with the complete structural formula. So I'm going to put an X here as like your starting point, and then you're going to work backwards. Now, and that's backwards from complete structural to the skeletal formula. Um, I am a big fan of writing out the complete structural formula because that gives me a way of looking at and seeing every atom that I need to see. Now, I think a good question at this point is, hey, when we take our quizzes or when we have an exam, can we use scratch paper? 100%. Um, I like to start out with my complete structural formula because then I can just go back and point to every single thing that I wanted to account for. Um, the condensed form and the structural form, well, the structural form is what I would say organic chemists love to draw because they will make a molecule that looks like this, and then they'll say boom, 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 and then oh well, here's this there, and then there's that there and that there, and at some point I'm just like, oh my gosh, this is insane. It's really tough to keep track of. And this right here could be a molecule. All of these points, whether it's this one or this one, they all correspond to carbons. And that's the important part about the structural formula. Now, another kind of display of a structural formula is if you have something like this. Let me ask you, how many carbons are in that structural formula? Add it to the chat. 4 is absolutely right. Okay. Now, if you were to write this as a structural formula or as a molecular formula, you'd say, well, 1, 2, 3, 4 carbons. And then this end right here and this end right here, where I've drawn these circles, there's going to be 3 hydrogens each. Okay, so that would be H3 there. So that's 6 hydrogens. Then here, where I'm putting an X now, I put a circle and I put an X, and now I'm putting another circle and I'm putting an X. At each one of those circles with the X's by them, how many hydrogens are going to be found on those carbons each? 2. Perfect. Because one of the things that we learned and then we revisited in this class, what we learned in 1310 and we revisited in this class was how many bonds does carbon like to form? 4. Now, if you're thinking about this and you're like, oh, I'm having trouble seeing some of these atoms, I'm going to take this molecule and draw it right here as the complete structural formula. And bear with me for just a second because I'm sorry I'm drawing this with a mouse, which I feel like is just as easy as drawing with a literal mouse, the rodent. Okay, so there's that. And then I've got nitrogen in the middle. And my bond lengths are not intended to be different. It's just, again, drawing with a computer mouse. Suppose it's better this than a trackpad. Okay, so there we go. Now, the last thing is that nitrogen really likes to have a lone pair of electrons, boom, boom, and then a hydrogen on it. Okay. So this molecule right here is basically the same, I'm going to draw that hydrogen there, as this molecule down in the lower left-hand corner. And I mean, I'll tell you guys that I like to draw that complete structural formula because it's easier for me to keep track of things. So then if I'm asked the question, how many hydrogens are found in this molecule? I can just do the simple thing and count them up. I can say, okay, well, here's 3, 4, 5, 6, 7, 8, 9, 10, 11. Done. That's what I like to do. Organic chemists, they would draw the molecule like this right here. Now, can I get a 1 if, hey, I follow that connection, or a 2, I don't follow that connection. I don't follow how those two are the same. Okay. So, and just so everybody knows, when I ask a question where I'm trying to get like a sense of where everyone is, um, usually, or what I like to do is I like to answer it or kind of go back through another walkthrough of it or conversation, talk about it, and then I move forward. If somebody has further questions on that same topic, please don't hesitate to drop by my office hours or email me and say, hey, can we meet at this time? Um, I just bring that up because I was looking at some of my evaluations recently, and I had somebody who was like, you assume that we know way too much and you never give a clear answer. And so I'm trying to address that, and that specifically. Like, that's my intention. I like to circle back, but then proceed. Um, okay, so when we look at, and you know what? I'm actually going to clear all the drawings on this slide. I think I'm confused by the points on the structural formula. I thought each point was a carbon. I got a private message. That was a private message. So let me show you structural formula, or the skeletal structure, I'll say, and I'm going to draw that same molecule. So here, what I'm going to try my, let's see, I'm really angry at my, uh, okay, we're good right now. So let's say that we have N, C, C, no, I'm going to do good over here. Sorry. N, C, 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 C. Okay. Now, if we look at each one of these carbons, each carbon likes to have a total of 4 bonds going to it. And I'm going to fill these bonds in just with hydrogens. So I'll take care of all my carbons, and they will have complete octets. Nitrogen doesn't like to have 4 bonds on it. It likes to have 3 bonds and a lone pair of electrons. So this nitrogen that's in the middle, it has 2 bonds. Now it's got a lone pair of electrons, and now it's got a hydrogen going to it. Converting that structure right there, I'm going to scribble this one out, to the skeletal structure. Well, it's going to look like this as a skeletal structure. Now, I could be wrong, but the person who sent the private message and they said, wait a minute, I thought all the points were a carbon. I feel like maybe what you're saying is, well, looking at that one, there it goes. Tablet. Yeah, throw this tablet away. Oh, dang it. I didn't mean to. Sorry, folks. Okay. So we've got, so converting this from the complete structural formula that I see to my skeletal structure. Okay. So that line right there denotes 2 carbons. This is 3 carbons. Now, if I put a nitrogen here and draw that, this nitrogen has replaced one of those 3 carbons. So this, what I've drawn right here, is 2 carbons and 1 nitrogen. If you follow that, could you give me a 7 in the chat? Okay. Then here, I've added this other little wing there. That also denotes 2 carbons. So now what I'm going to do is add my lone pairs of electrons and the hydrogen down here. And this structure right here corresponds to or is the same as this structure up here. Now, the person who sent me the private message, did that provide any clarity, or anyone else who is confused about this? Did this help? Give me a Y or N to the chat. Okay. Okay. So that's just something to kind of navigate. More times than not, your questions are going to involve the complete structural formula as opposed to the skeletal structure. But I do want you to be able to, like, if you see a structural formula, sorry, a skeletal structure, this guy right here, to be able to match these two or match these, kind of go between all of these. And some folks, as they get more adept at this, they skip some of those steps. I don't, you don't need to. It's not going, nobody's going to get style points on an exam because they skipped a test, skipped a step for themselves. Okay, so aliphatic hydrocarbons. Now, we are going to use the stems, those 1 through 10s, plus the suffix ane, propane. Okay, so methane is methane. Now, these hydrocarbons or these carbons are going to be saturated, which means any place that they don't have a bond, there's going to be a hydrogen there. So methane, for example, that's 1 carbon. That's not bound to anything else. So it's that central carbon is bound to nothing else like another oxygen or like another carbon or an oxygen. It's going to instead have 4 hydrogens coming off of it. Ethane, well, that's 2 carbons. And everywhere we can put an atom, we're going to put a hydrogen. So C2H6. Propane, 3 carbons and 8 hydrogens. Butane, 4 carbons and 10 hydrogens. Now, there is a calculation or a formula for doing these, and that is C followed by N, the number of carbons, and then H followed by 2 times N plus 2. So if you had a 64 carbon molecule, that would be C64, H 130. Because 2 times 64 equals 128 plus 2 equals 130. Okay, so some things that I want you to take away from this. If you are talking about an alkane, well then, think CnH 2 times N plus 2. I didn't need the parentheses here, but it's there. In addition to that, could you tell me what kind of bond is this? And I'm thinking, is it like number? That's a single bond. So if you have a molecule that has nothing but single bonds, that is an alkane. So nothing but single bonds. Now, with that in mind, if we had a molecule that had a double bond, do you think that this molecular formula is still going to be valid for it? It's not. So we're going to get to that in just a little bit. But before we do, I want you to look at this table. Here's our molecules that we're most interested in. Methane down to decane. And the example that I'd like you to think about here is I want you to compare octane and butane or octane and propane. Okay, we drew the connection earlier that octane, something you get at the gas pump. If you spilled that on the ground, and let's say that it's a nice brisk July day of humidity of 95 and the low temperature for the day is 78, but the high in the middle of the day is 102. If you spilled some gasoline, like you're filling your car up and you spill a little bit of gasoline on the ground, you spilled a liquid on the ground. Okay. Now, what's going to happen to that liquid pretty darn quickly? It's going to evaporate. Now, if you at the same time went over to HEB and you got a propane canister and you picked it up and you shook it around, do you think that you'd hear sloshing of a liquid in there? Wire end to the chat. Like, would it sound like? No. Same thing goes with butane. And the reason for that, and what I want you to think about, is the melting point right here. So, where we go from a liquid to a solid, the melting point for propane and butane is negative 188 and negative 138 degrees Celsius. Now, where we go from a liquid to a gas, our boiling point is negative 42 and 0 degrees Celsius. Um, so if it's 95 degrees Fahrenheit outside, is that higher than these two boiling points? Wire end to the chat. 95 Fahrenheit. Is that higher than negative 42 Celsius and 0 Celsius? Yeah, it's going to be much higher. So my point is that propane and butane, those are going to be gases at room temperature. So those are going to be like aerosolized. Whenever I say gases, I'm not talking about like gasoline. I'm talking about if you were to open that propane tank valve, a gas is going to spray out of there. It's not going to be a liquid that sprays out of there. Now, octane, 126 degrees Celsius. So that will not convert from a liquid to a gas until you're at 126 degrees Celsius. So at room temperature, I'm going to say a liquid at RT, or room temperature. Now, with that in mind, if you look over at this last column, use or occurrence, we've got starting with pentane all the way down to dodecane. These are all gasoline components. So what I was talking about earlier with respect to a octane rating, well, if you go and get gasoline today, it's a mixture of lots of stuff. It's a mixture of octane, heptane, hexane, pentane, decane, dodecane. If you go and get that highest octane rating, well, more than likely you're going to have a lot of octane. Are you going to have other compounds in there? Yeah, but octane is going to be in a higher amount. Okay, so these are our alkanes. Now, alkanes can have modifications to them. And these modifications are known as alkyl substituents. These modifications, if you have a CH3, that's what's known as a methyl group, an ethyl group, an N-propyl group, or an N-butyl group. Now, where I'm going with this is nomenclature. So if you look at this molecule right here, I hope that everyone can count this up and say, okay, well, here's 1 carbon, 2 carbons, 3, 4, 5, and 6. We got 6 carbons on there. Now, with that, we've got this different numbering scheme that is 1, 2, 1, 2, 3, 4, 5. Why is 1 listed twice? Well, the reason that one is listed twice is because the way that we name an organic molecule necessitates or requires us to list that one twice. What we want to do is we want to identify the parent chain. So another way of putting that is, what's the longest carbon, I'll say carbon-carbon chain? That's our question. After you've done that, you want to number the atoms in that chain. And in this case, whether we start from here or we start from here, we're going to come up with a chain that is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. So whenever you're doing this sort of thing and identifying your longest possible chain, what you want to be able to do is distinguish between, well, what is a part of the chain and what is a substituent or what is a modification to that. Now, when you do that, I think that it's pretty fair to say, well, why couldn't we go 1, 2, 3, 4, 5, 6? Why couldn't we do that? And the answer, to put it bluntly, is, well, that's not the convention. Those are against the rules. So our rule is we find the longest possible chain and we go from there. Now, we've got a 5-carbon chain here, and then we've got a modification on it. So could everyone give me a 5 in the chat if they can see the 1 or the 5-carbon chain and understand that as opposed to 6 or anything like that? Okay. Now, what we want to do, I'm going to scribble these out just for a moment. Is we want to look at this 5-carbon chain and say, okay, well, we need to account for that 6th carbon. So what we do is we refer to this one right here as a methyl group. Now, that's a methyl group because it is only 1 carbon. It is this right here. So we've made our 5-carbon chain and we see 1 carbon popping off of that. That is our methyl group. So this guy right here is our methyl group. Now, what we're aiming to do is we want to give this methyl group the lowest possible number. So the lowest possible number is going to be achieved when we start down here. If we started our numbering right here, where would we put our methyl group? What number would we give for our methyl group? If we started over here, this would be carbon 1, 2, 3, 4, 5. So we would say, well, this is 4-methyl because our methyl group is found on carbon number 4. Does that make sense? Give me a Y or an N to the chat. Okay. But if we started on this end where the carbon number 1 is in red, we'd say 1, 2, 3, 4, 5. So whenever you look at a molecule, you have to assess, okay, well, what is my carbon number going to be? Where is my modification going to be? Does that make sense? Give me a Y or an N to the chat. Okay. So if we had something like this right here, we've got 1, 2, 3, 4, 5, 6, 7, 8. This molecule right here is octane. That's all there is to it. It's 8 carbons, not a single double bond or anything like that. Now, if we had 1, 2, 3, 4, okay? We've got 1, 2, 3, 4 carbons coming off of this. Now, what we would want to do is redo our numbering and say, okay, well, where is this one? We've got this modification. We started this numbering where we went left to right, but is that the best numbering that we can come up with? Well, if we did that, let's see. The first thing that we need to do is get our longest possible chain. So I'm going to use this as number 6, 7, 8, 9, and 10. Okay. So is it best to call this molecule octane, or is there another name that we should give this molecule? Spoiler alert. Octane's not best because that's not our longest possible chain. What's our longest possible chain from this? How many carbons is it? Oh, decade. Perfect. 10 carbons. Okay. So we've got this chain right here. I'm going to circle it. This is 10 carbons. Is everyone good with that? Give me a Y or an N to the chat. Okay. Now, we changed our numbering, but we don't want to completely neglect these two. So what we do is we say, all right, well, these two carbons make up a ethyl group. So we're going to call this, using this kind of model, we're going to call it decane. That's our longest possible chain is 10 carbons. That's why we've got decane. But it's decane with an ethyl group on it. So we're going to call it ethyl decane. Does everyone follow that? Give me a Y or an N to the chat. Now, next question, Y or N to the chat. Do we need to put a number on here? Would that be helpful to kind of distinguish or identify where that ethyl group is? Absolutely. So what number are we going to put? We want to give this ethyl group the lowest possible number. Okay, got to vote for 2. Well, remember, we got to keep our numbering from our longest possible chain. So it could be 6, because carbon number 6 is where that ethyl group is coming from. Alternatively, we might have to look at our other numbering. Starting over here, that's 1, 2, 3, 4, and 5. So the best name for this would be 5-ethyl decane. Okay, give me a 1 if you got it all. Yeah, that all makes sense. A 2 if you were with me with ethyl decane, or a 3 if you were just with me for decane. 1 if you got it all. 2 if you're like, I got ethyl decane. And 3, I just got decane. Okay. And I think a part of the confusion is probably because of my technical issues that I'm encountering with my erasing. And that is making me very angry. But I'm controlling my emotions right now. Oh, dang, that's not okay. So I apologize, but here's okay. So we've got 1, 2. Joel, computer. I just pressed erase all ink on slide and something showed up. I'm sorry. Okay, so we've got carbon number 1, 2, 3, 4, 5, 6. Okay, I'm going to go to the discard my annotations. Share my screen. Okay. So we go back and we make our decane molecule. 1, 2, 3, 4, 5, 6, 7, 8. There's our 8 carbons, but then we had this 1, 2, 3, 4. Okay, so what we need to do is start our numbering here. 1, 2, 3, 4, 5. 5 is where we have this ethyl group, this 2-carbon chain that comes off of that. That's why we call it 5-ethyl decane. Okay, so now our sequence is we have to find our longest parent chain. We have to find the longest carbon-carbon chain. Then we have to number it. That's where we come up with our prefixes. Then we have to name anything that's added to it, assign a number to whatever is added to it, and complete the name. So if we look at these structures right here, we're going to go one by one. Starting on the far left. If we start here, or if we start here, I'm going to do this in red. I'm going to have numbering in red with one starting point, and then I'm going to change my color and do a different numbering. 1, 2, 3, 4, 5. Okay, so that gives us 5 carbons. Now I'm going to switch to green. If we started here, 1, 2, 3, 4, 5. This is a pentane. So pentane. Okay. Our longest possible chain is 5 carbons. Now, if I started on the green numbers, 1, 2, 3, 4, 5, got it. Okay. Now, if I started with the red numbers, well, I'd start over here and it'd be 1, 2, 3, 4, 5. But my eyes aren't deceiving me. There are a total of 6 carbons in this molecule. Now, I'm going to go with my red numbering. It doesn't matter if I selected the red or the green because they're effectively the exact same. Now, going with my red numbering, there is a single carbon that comes off of carbon number 2. When you have a single carbon, a single CH3, it's common to call that a methyl group. So this molecule is methylpentane. Because I saw this modification or this group coming off of carbon number 2. It's just CH3, so that is methyl. So this is methylpentane. Is everyone good with that? Okay. Now what I need to do is say, all right, well, that's methylpentane, but where is that methyl group? Because if you look at this right here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. One too many, sorry. 1, 2, 3, 4, 5. Okay, so that's pentane. Is this right here also methylpentane? It is. So this is also methylpentane because I've got a 5-carbon chain and then I've got this methyl group coming off of it. We need to be able to distinguish between these two molecules. And so this right here in the upper left-hand corner, that's going to be 2-methylpentane. This one right here, the one that's all in red, is methylpentane. And ane, but it is 3-methylpentane. Could you give me a Y or an N in the chat if you follow that? Okay, great. Now, tell me in the chat what is the longest possible chain that you can come up with for this molecule? Perfect. Octane. Okay, so we're going to start at the end. We're going to call it octane. All right. Now, How many carbons does this molecule have? Well, it's got 9. So we need to account for that 9th carbon. So how would we account for that one? Spoiler alert, very similar to how we did the last one. We'd call this methyl octane. Now we want to give that methyl group the lowest possible number. How are we going to do that? Well, we call it, if this is 1, that's 2, 2-methyl octane. Okay. Now this one right here, this next molecule, is a little bit trickier. So I always like to just start on the left and move to the right. 1, 2, 3, 4, 5, 6. 6 carbons. But I also have a couple of other points that I could start with. 1, 2. No, that's if I went to the left, that'd be 3, 4. So those aren't good. So I'm going to erase that, that, and that. So this is hexane. So I'm going to write hexane. Now, what I have though is I've got, this is a methyl group, and this is a methyl group, because those are both points that account for carbons. Could you give me a Y or an N if you follow that? Okay. Now, could anyone tell me, with the carbon numbering as my kind of landmark, where are those methyl groups? Carbon number 3. I like it. So what we want to do is I'm going to say methyl, because it is a methyl group. I used methyl over here, and I was indicating one methyl group. I've got 2 methyl groups here. And the way that I want to clarify that is by saying dimethyl. Now, to really hammer home this point, I want to indicate where those methyl groups are. There are 2 of them, which is why I included di. And then I want to include the numbers. So 3, 3 dimethyl hexane. Does that make sense? Give me a Y or an N in the chat if that makes sense. Okay. Now, one of the things that I want you to think about with respect to this is, well, what if, or could there be a molecule that has multiple methyl groups and they're not on the same carbon? 100%. If you had, let me show you, I'm going to try to draw this structure very similar to what you see above. Okay. There is, drawn with a mouse, there is my best representation of this hexane and a methyl group on carbon number 3. Here's a methyl group on carbon number 4. So this molecule that I've just drawn, and sorry for my poor drawing, this is dimethylhexane. Does everyone see that? Give me a 7 in the chat if you see it. Okay, great. Seeing lots of responses there. This is dimethylhexane. We would refer to this as 3,4 dimethylhexane. Dimethyl dot dot dot. Okay. So you use the numbers to indicate where these groups are. And this is an example of an alkane and alkane numbering. I think that for what is expected of you guys, I would get comfortable with some of these substituents, and I will give you some practice examples using these different modifications. Now, with that said, your longest chains that you're going to deal with are 10 carbons. So I'm not going to give you anything more than that. But I want you to be most comfortable with methyl and ethyl groups. Okay. Now, these isopropyl, isobutyl, T-butyl, sec-butyl, those are kind of names that are also names that are used for these. I want you guys to be most comfortable with methyl and ethyl. Okay. And whenever I talk about methyl groups and ethyl groups and say, oh, I want you to be comfortable with methyl and ethyl, I always feel like I'm talking about these are two people who live at a retirement community who are very friendly. This is Ethel, and this is her friend Methyl. Um, at any rate, now we're moving on to alkenes. Alkanes, now onto alkenes. Use the stem and then ENE. So the difference between these name-wise is a single letter. Alkenes contain at least one double bond. So is it possible to have a molecule of methene? Think about meth, not the drug, but think about methane. Methane only has one carbon. In order to have a double bond, you have to have two or more carbons. So methene is literally impossible. Now, carbons with a double bond are considered to be unsaturated. That means they are bound to carbon and they don't have any hydrogen. This question down here is the one that I was asking. Can methene exist? No. An alkene is defined by a double bond between two carbon atoms. Methyl groups only have one carbon and thus can never have a double bond to a carbon. So methene cannot exist. Now, the calculation or the formula calculation for alkenes is CN2HN, or sorry, H2N, sorry. So we've got ethene right here, two carbons, double bond there. Here is another model for ethene. We've got the skeletal structure versus the complete molecular formula. If you take C2H2 times 2, you get, well, CH4, or C2H4, sorry. Propene, that is 1, 2, 3 carbons. How many hydrogens? Well, it's going to be 3 times 2, or 6. So C3H6. Now, alkenes can get a little bit complicated. Here, what we have, starting on the far left, we've got 1. I always like to start on the left-hand side of the molecule. 1, 2, 3, 4, 5, and 6. Okay, 6 carbons, hex. Oh, there's 1 double bond, hexene. 2 methyl, 3 hexene. Oh man, how do we do that? Okay, so 1, 2. Okay, carbon number 2 is a methyl group. Carbon number 3 is where we find our double bond. So this 3 indicates where your double bond is. So 3 hexene. So this 3 applies to that ENE, essentially. The 2 responds to, or is responsive to, the methyl group. Now, our next molecule, 2-ethyl 1-pentene. Okay, what we're looking at there then is our longest possible chain is 5 carbons. Okay, 1, 2, 3, 4, 5. Okay, I see 5 there. But then let's think about this. 1, 2, 3, 4, 5, 6. Wait a minute. That's 6 carbons. But, that's 6 carbons. Shouldn't that be a hex? It's a good way to think about that, but this particular example, it should not be. This is a pentene. The reason why is because what you want to do is you want to give this ENE and this ethyl the lowest possible group or lowest possible numbers. So the numbering here actually starts here. 1, 2, 3, 4, 5. Now, this particular question, this particular example is kind of a next level question. This would be the sort of question where I would show you a molecule and say, what is the name for this? And give you this as an example. Because this is so the kind of origin of this is you're giving this the ENE, its lowest possible number, and then you're giving the ethyl group, which is right here, lowest possible number of 2. Now our next one is even more complicated. This is 2-methyl 1,3-butadiene. Oh man. Okay. So bute, let's jump back. Bute corresponds to 4 carbons. Butane is 4 carbons. Butene is 4 carbons. Butadiene. Diene indicates that you have 2 double bonds. There's one. There's the other. Okay. Now we've got 4 carbons on this molecule, though. I'm going to erase those. And now what I'm going to do is say, okay, well, we've got 1, 2, 3, 4. Well, this double bond with the name 1,3-butadiene, we get one of those double bonds that have the lowest possible number of 1. That leads to our methyl group being found on carbon number 2. And then our other double bond is found on carbon number 3. Now, if you're looking at that and thinking, oh, but well, how else could I name it? Well, let's try starting over here. 1, 2, 3, 4. If we had our numbering start like that, how would this name be different? Well, it's still butadiene. Is everyone good with the butadiene? Give me a 9 in the chat if you follow butadiene. Okay. Now, if we use this green numbering, it would still be 1, 3 butadiene. Does everyone agree with that? If so, give me an R in the chat. Okay. So we've got 1,3-butadiene. The difference would be, well, this would be 3-methyl. 3-methyl 1,3-butadiene. And it's this right here, this 2-methyl, that is kind of why this name is preferred. We can get the methyl group to have a lower number. And that's kind of our objective. We want to give any of these functional groups the lowest possible number. Okay. Now the last group of molecules, or sorry, the second to last group of molecules are known as alkynes. So if you're like, what's a good takeaway from today? We have alkanes, alkenes, alkynes. Alkanes, you've got nothing but single bonds. Alkenes, you've got at least 1 double bond. An alkyne, you have at least 1 triple bond. There's no such thing as a quadruple bond, so you don't even have to worry about that. Now, the molecular formula calculation is CnH2n minus 2. Here what we've got is 1-butyne, 2-butyne, ethyne. Ethyne is 2 carbons and a triple bond between those 2 carbons. 2-butyne. Well, that would be a triple bond between carbons number 2 and 3 in a 4-carbon molecule. One butene would look like this. 1, 2, 3, and there. That's one butene. And that's also what is drawn right here. Okay. Now, our last piece of information, or our last group that I want to talk about before I put the closer questions up, is our cyclic hydrocarbons. So, cyclopentane, well, that's 5 carbons, but it's a ring, hence cyclo. Cyclohex, 6 carbons, ENE, hexene. Cyclopropane, cyclohexane, cyclobutane, cyclooctane. So anytime you see those names like cyclo, just think, okay, it's a ring. Now, a fair question, or one of the, it's not really a trick question, but well, yeah, I guess it is a trick question. Um, can you form, or how many carbons are needed to form a ringed molecule or to form a cyclic hydrocarbon? More than one. Can you form a ring with 2? Nope. You need to have at least 3 carbons to form a cyclic molecule. Cyclopropane. So the smallest possible ring is made up of 3 carbons. All right. So when it comes to like this sort of question, naming a molecule, you'll probably have one of each one of these. Think about having one of each one of these on an exam or a quiz or something like that. I will give you some examples. I'm writing this as a note for myself. Um, I'll give you some nomenclature practice problems. And these will be things that are just kind of ungraded, and I'll give you those and find it and get a key for them. But in the meantime, that's all that I've got. So what I'm going to do now is launch the closer questions. And so whenever you answer these, you're free to go, and I hope you have a wonderful afternoon. I have office hours starting in about 18 minutes. I'm going to end my slideshow. And, provided that you participate in one of the poll questions, everyone's going to get 2 points for participation. I should have those up to date by Wednesday. Okay, well, thank you guys very much for coming to class, and I hope you have a great day.